Some basic concept of chemistry. Chemistry is the science of molecules and their transformation. It is the science not so much of 100 elements but of the infinite variety of molecules that may be built from them. Science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and change in them in daily life. Curd formation from milk, formation of vinegar from sugar cane juice, on keeping for prolonged time and rusting of iron are some of the examples of change which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure and reactions of material substances is called chemistry. Development of chemistry. Chemistry as we understand it today is not a very old discipline. Chemistry was not studied for its own sake. Rather, it came up as a result of search for two interesting things: philosopher's stone pans, which would convert all baser metals, as example iron and copper, into gold; elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and electrochemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe after a few centuries of alchemical traditions which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indians, had their own alchemical traditions. These included much knowledge of chemical process and techniques. In ancient India, chemistry was called Rasayan Shastra, Ras Tantra, Ras Kriya or Ras Vidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavation at Mohenjo-daro in Sindh and Harappa in Punjab proved that the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction work. It showed the mass production of poetry, which can be regarded as the earliest chemical process in which material were mixed, molded and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery has been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains lime sand and traces of CaCO3. Harappans made fans, a sort of glass which was used in ornaments. They melted and forged a variety of objects from metals such as lead, silver, gold and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Maxi in South India 1000 to 900 BCE and Hastinapur and Taxila in North India 1000 to 200 BCE. Glass and glaze were colored by addition of coloring agent like metal oxides. Copper metallurgy in India dates back to the beginning of Chalcolithic culture in the subcontinent. There are much archaeological evidence to support the view that technology for extraction of copper and iron were developed indigenously. According to Rig Veda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BC. The golden gloss of the black polished way of northern India could not be replicated and is still a chemistry mystery. These wares indicate the mastery with which clean temperatures could be controlled. Kautilya's Astra Shastra described the production of salt from sea. A vast number of statements and material described in the ancient Vedic literature can be so to aggravate modern scientific findings. Copper utensils, iron, gold, silver, ornaments and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Sutra Samhita explains the importance of alkalis. The Charka Samhita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc, the sulfates of copper, zinc, and iron, and the carbonate of lead and iron. Panisara described the preparation of gunpowder mixture. Tamil texts also describe the preparation of firework using sulfur, charcoal, saltpeter, potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a reputed chemist, an alchemist, and a metallurgist. His work Rastantkar deals with the formulation of mercury compounds. He has also discussed methods for the extraction of metals like gold, silver, and tin and copper. A book, Sarnavam, appeared around 800 CE. It discusses the use of various furnaces, ovens, and crucibles for different purposes. It describes methods by which metals could be identified by flame color. Sarkapani discovered mercury sulfide. Thus, credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredient for making soap. Indians began making soap in the 18th century CE. Oil of erenda and seeds of mahua plants and calcium carbonate were used for making soap. The paintings found on the wall of Ajanta and Ellora, which look fresh even after age, testify to high level of science achieved in ancient India. Brahmihir Brihat Samhita is a sort of encyclopedia which was composed in the 6th century CE. It's informed about the preparation of glutinous material to be applied of walls and roofs of houses and temples. It was prepared entirely from an extract of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such materials scientifically and assess them for use. A number of classical texts like Atharvaveda 1000 BC mention some dye stuff. The material used were turmeric, madder, sunflower orpiment, cochineal, and lac. Some other substances having tannin property were camplesia, patanga, and jatuka. Brahmihir Brihat Samhita gives reference to perfume and cosmetic recipe for hair dyeing were made from plants. Like indigo and mineral like iron powder, black iron or steel, and acidic extract of sour rice gruel. Gandhayukli describes recipe for making scent mouth perfumes, bath powder, incense, and talcum powder. Paper was known to India in the 17th century as account of Chinese traveler purchasing describes. Excavation at Taxila indicate that ink was used in India from the 4th century. Color of ink were made from chalk, red lead, and many more. It seems that the process of fermentation was well known to Indians. Vedas and Kautilya's Astra mention about many types of liquids. Charanka Samhita also mentions ingredients such as bark of plants, stem, flower, leaves, wood, cereals, fruits, and sugar cane for making asbestos. The concept that matter is ultimately made of indivisible building blocks appeared in India a few centuries BCE as a part of philosophical speculation. Archaea, Canada, born in 600 BCE, originally known by the name Kasyap, was the first proponent of the atomic theory. He formulated the theory of very small indivisible particles, which he named Pramanu, comparable to atom. He authored the text Vaisika Sutras. According to him, all substances are aggregated from the form of a smaller unit called atom Pramanu. which are eternal, indestructible, spherical, supersonible, and in motion in the original state. He explained that this indivisible entity cannot be sensed through any human organ. Canada added that there are varieties of atoms that are as different as the different classes of substances. He said these Parmanu could form pairs or triplets, among other combinations, and unseen forces causes interaction between them. He conceptualized this theory around 2500 years before John Dalton, 1766 to 1844. Charaka Samhita is the oldest Ayurvedic epic of India. It describes the treatments of diseases. The concept of reduction of particle size of metals is clearly discussed in Charaka Samhita. Extreme reduction of particles size is termed as nanotechnology. Charaka Samhita describes the use of bhasma of metals in the treatment of ailments. Nowadays, it has been proved that bhasma has nanoparticles of metals. After the decline of alchemy, electrochemistry reached a steady state, but it too declined due to the introduction and practice of the Western medicinal system in the 20th century. During this period of astigmatism, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It looks about 100 to 150 years for Indians to learn and adopt new techniques. During this time, fragrant product poverty. As a result, indigenous traditional technique gradually declined. Modern science appeared in Indian science in the later part of the 19th century. By the mid-19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that chemistry deals with the composition, structure, properties, and interactions of matter and is of much use to human beings in daily life. These aspects can be best described and understood in terms of basic constituents of matter that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can be seen, weigh and perceive these entities. Atom and molecules. Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of these particles? We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical value with suitable units. Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain, and operation of a computer, production, and in chemical industries. Manufacturing, fertilizer, alkalis, acids, salts, dyes, polymers, drugs, soap, detergent, metals, alloy, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human need for food, healthcare product, and other material aimed at improving the quality of life. This is exemplified by the large-scale production of a variety of fertilizer, improved variety of pesticides and insecticides. Chemistry provides methods for the isolation of life-saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and taxol, which are effective in cancer therapy. The drug AZD is used for helping its practitioner. Chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having specific magnetic, electric and optical properties. This has led to the production of superconducting ceramic, conducting polymer, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymer metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternative to environmentally hazardous refrigerant like CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere, having successfully synthesized. However, many big environmental problems continue to be matter of grave concern to the chemist. One such problem is the management of the greenhouse gases like methane, carbon dioxide, etc. Understanding a biochemical process, use of enzymes for large-scale production of chemicals, and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concept of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies a space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of a state of matter which you learned in your previous classes. 1.2.1 States of matter. You are aware that matter can exist in three physical states with solid, liquid and gas. The constituent particles of matter in these three states can be represented as so in figure 1.1. Particles are held very close to each other in solids in an orderly fashion, and there is not much freedom of movement. In liquid, the particles are close to each other but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states, and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. Solid have definite form and definite shape. Liquid have definite volume but do not have definite shape. They take the shape of the container in which they are placed. Point 3. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the condition of temperature and pressure. On heating, a solid is usually changed to a liquid, and the liquid on further heating changed to gas or vapor. In the reverse process, a gas or on cooling liquefies to the liquid, and liquid on further cooling freezes to the solid. 1.2.2 Classification of matter. In class 9 chapter 2, you have learned that the other microscopic or bulk level matter can be classified as mixture of pure substance. These can be further subdivided as shown in figure 1.2. When all constituent particles of a substance are same in chemical nature, it is said to be pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substance which may be present in it in any ratio. Hence, their composition in variable pure substance forming mixture are called its components. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles or components of the mixture are uniformly distributed throughout. The bulk of the mixture and its composition is uniform throughout. Sugar solution and air are the examples of homogeneous mixture. Each contrasts to this. In a heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixture of salt and sugar grains and pulses along with some dead often stone pieces. A heterogeneous mixture. You can think of many more examples of mixture which you come across in the daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple hand picking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixture. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water and glucose are some examples of pure substances. Glucose contains carbon, hydrogen and oxygen in a fixed ratio and its particles are of same compositions. Hence, like all other pure substances, glucose has a fixed composition. Also, its constituents, carbon, hydrogen and oxygen, cannot be separated by simple physical methods. Pure substances can further be classified into elements and compound. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atom and molecules from the previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. They all atoms are of one type. However, the atoms of different elements are different in nature. Some elements such as sodium or copper contain atoms as their constituent particles, whereas in some other the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen and oxygen gases consist of molecules in which two atoms combine to give their respective molecules. This is illustrated in figure 1.3. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituent of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Examples of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in figure 1.4. Note that a water molecule comprises two hydrogen atom and one oxygen atom. Similarly, a molecules of carbon dioxide contain two oxygen atom combined with one carbon atom. Thus, the atom of different elements are present in the compound in a fixed and definite ratio, and this ratio is characteristics of a particular compound. Also, the properties of a compound are different from those of its constituent element. For example, hydrogen and oxygen are gases, whereas the compound formed by their combination, as example, water is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a sputter of combustion. But water is used as a fire extinguisher. 1.3 Properties of matter and their measurement. 1.3.1 Physical and chemical properties. Every substance has unique or characteristics properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acid and bases, etc. Physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement or observation of chemical properties require a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The example of chemical properties are characteristics reaction of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. 1.3.2 Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and meter denotes meter, the unit in which the length is measured. Earlier, two different systems of measurement, the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in the late 18th century, was more convenient as it was based on the decimal system. Late need of a common standard system was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. 1.3.3 The International System of Units. The International System of Units, in French, Le Système International des Units, abbreviated as SI, was established by the 11th General Conference on Weight and Measures (CGPM) from Conference General des Poids et It measures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as Meta Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in table 1.1. These units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. The definition of the SI base unit are given in table 1.2. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in table 1.3. Let us now quickly go through some of the quantities which will be often using in this book. 1.3.4 Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to changing in gravity. You should be careful in using this term. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. The SI unit of mass as given in table 1.1 is kilogram. However, its fraction may name as gram. 1 kilogram is equal to 100 gram. Is used in laboratories due to the smaller amounts of chemical used in chemical reaction. 1.3.5 Volume. Volume is the amount of space occupied by a substance. It has the unit of length Q. So in SI system volume has units of meter cube, but again in chemistry laboratories smaller volume are used. Hence volume is often denoted in centimeter cube or dm³ units. A common unit liter L, which is not an SI unit, is used for measurement of volume of liquids. In the laboratory, the volume of liquid or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in figure 1.7. 1.3.6 Density. The two properties, mass and volume, discussed above are related as follows. Density is equal to mass by volume. Density of a substance is its amount of mass per unit volume. So SI unit of density can be obtained as follows. The SI unit of density, SI unit of mass by SI unit of volume. Kilogram by meter cube or kilogram meter cube. This unit is quite large and a chemist often expresses density is the cm³ minus q, centimeter minus q, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. 1.3.7 Temperature. These are three common scales to measure temperature: degree Celsius, Fahrenheit, and Kelvin. Here Kelvin is the SI unit. The thermometer based on these scales are shown in figure 1.8. Figure 1.8. Generally, the thermometer which is Celsius scale are calibrated from 0 degree to 100 degree, where these two temperatures are the freezing point and the boiling point of water, respectively. The Fahrenheit scale is represented between 32 degree to 212 degree. The temperature on the two scales are related to each other by the following relationship. Fahrenheit is equal to 9/5 degrees Celsius plus 32. The Kelvin scale is related to Celsius scale as follows. Kelvin is equal to degree Celsius plus 273.15. It is interesting to note that temperature below 0 degrees Celsius negative values are possible in Celsius scale, but in Kelvin scale negative temperature is not possible. 1.4 Uncertainty in temperature. Many a time in the study of chemistry has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the number of conveniently and present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. 1.4.1 Scientific Notation. As chemistry is the study of atoms and molecules which have extremely low masses and are present in extremely large number, a chemist has to deal with number as large as 600 to 218 for the molecules of 2 grams of hydrogen gas, or as small as 0.230166 gram mass of each atom. Similarly, other constants such as Planck's constant, speed of light, charge on particles, etc. involve number of the above magnitude. It may look funny for a moment to write a count number involving so many zeros, but it often a real challenge to do simple mathematical operations of addition, subtraction, multiplication, or division with such number. You can write any two numbers of the above type and write any one of the operations you look to accept as a challenge, and then you will really appreciate the difficulty in handling such number. This problem is solved by using scientific notation for such number exponential notation in which any number can be represented in the form n into 10n, where n is an exponent having positive or negative value and n is a number called digit term, which varies between 1.000 and 9.999. Thus, we can write 232.508 as 2.32508 into 10 to the power 2 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and same is the exponent to obtain in the scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 to the power minus 4. Here, the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the scientific notation. While performing mathematical operations or number expressed in scientific notation, the following points are to be kept in mind. Multiplication and division, these two operations follow the same rules which are there for exponential number as example. Addition and subtractions. For these two operations, first the number are written in such a way that they have to same exponent. After that, the coefficient digit terms are added or subtracted as the case may be. Thus, we are adding 6.65 into 10 to the power 4 and 8.95 into 10 to the power 3. Exponent is made the same for both the numbers. Thus, we get 6.65 into 10 to the power 4 plus 0.895 into 10 to the power 4. Then this number can be added as follow. Similarly, the subtraction of two numbers can be done as below. 1.4.2 significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitations of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and comes out to be 9.4 gram. On measuring the mass of this object on an analytical balance, the mass obtained is 9.4213 gram. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or the calculated value is indicated by maintaining the number of significant figures. Significant figures are meaningful digits which are known with certainty plus or one which is estimated or uncertain. The uncertainty is indicated by writing the certain digit and the last uncertain digit. Thus, if we write a result as 11.2 ml, we say the 11 is certain and 2 is uncertain, and the uncertainty would be plus 1 in the last digit unless otherwise stated, and uncertainty of plus minus 1 is the last digit is also understood. There are uncertain rules for determining the number of significant figures. These are stated below. All non-zero digits are significant. For example, is 285 centimeter. There are 3 significant figures, and in 0.25 ml there are 2 significant figures. 0.2 preceding to first non-zero digit are non-significant. Such 0 indicates the position of decimal point. Thus, 0.002 has 1 significant figures and 0.0052 has 2 significant figures. 0.3 zeros between 2 non-zero digits are significant. Thus, 2.005 has 4 significant figures. 4.0 as at the end or right of a number are significant, provided the they are on the right side of the decimal point. For example, 0.200 gram has 3 significant figures, but if otherwise the terminal 0 are not significant if there is no decimal point. For example, 100 has only 1 significant figure, but 100 has 3 significant figures, and 100.0 has 4 significant figures. Such numbers are better represented in scientific notation. We can express the number as 100 as 1 into 10 power 2 for 1 significant figure, 1.0 into 10 power 2 for 2 significant figures, and 1.00 into 10 power 2 for 3 significant figures. Point 5. Counting the numbers of objects, for example 2 balls or 20x. Have infinite significant figures, or these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal. Example, 2 is equal to 2.000000 or 20.000000. In number detail, in scientific notation, all digits are significant. Example, 4.01 into 10 power 2 has 3 significant figures, and 8.256 into 10 power minus 3 has 4 significant figures. However, one would always like the result to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements of same quality. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value for a result is 2.00 gram and a student takes 2 measurements and reports the result as 1.95 gram and 1.93 gram. These values are precise as they are close to each other but are not accurate. Another student B repeats the experiment and obtains 1.94 gram and 2.05 gram as the result for 2 measurements. These observations are neither precise nor accurate. When the third student C repeats these measurements and reports 2.01 gram and 1.99 gram as the result, these values are both precise and accurate. These can be more clearly understood from the data given in 1.4 table. Addition and subtraction of significant figures. The result cannot have more digits to the right of the decimal point than either of the original number. Here 18.0 has only 1 digit after the decimal point, and the result should be reported only as up to 1 digit after the decimal point, which is 31.1. Multiplication and division of significant figures. In this operation, the result must be reported with no more significant figure as in the measurement with the few significant figures. 2.5 into 1.25 is equal to 3.125. Since 2.5 has 2 significant figures, the result should not have more than 2 significant figures. Thus, it is 3.1. While limiting the result to the required number of significant figures as done in our mathematical operation, one has to keep in mind the following point for rounding off the number. 1 point. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. For example, 1.386. If we have to remove 6, we have to round it to 1.39. Point 2. If the rightmost digit to be removed is less than 5, the preceding number is not changed. For example, 4.334 is to be removed, then the result is rounded up to 4.33. Point number 3. If the rightmost digit to be removed is 5, then the preceding number is not changed if it is an even number, but it is increased by 1 if it is an odd number. For example, if 6.35 is to be rounded by removing 5, we have to increase 3 to 4, giving 6.4 as the result. However, if 6.25 is to be rounded off, it is rounded off to 6.2. 1.4.3 Dimensional analysis. Often while calculating, there is a need to convert units from one system to the other. The method used to accomplish this is called factor level method or unit factor method or dimensional analysis. This is illustrated below. Example: a piece of metal is 3 inches represented by n long. What is its length in centimeter? 1.5 Law of chemical combination. The combination of elements to form compound is governed by the following 5 basic laws. 1.5.1 Law of conservation of mass. This law was put forth by Antoine Lavoisier in 1789. He performed careful experimental studies for combustion reaction and reacted to the conclusion that in all physical and chemical changes there is no net change in mass during the process. Hence, he reached to the conclusion that matter can be neither be created nor destroyed. This is called law of conservation of mass. This law formed the basis of several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactant and product and carefully planned experiment performed by Lavoisier. 1.5.2 Law of definite proportion. This law was given by a French chemist Joseph Proust. He stated that a given compound always contains exactly the same proportion of element by weight. Proust worked with 2 samples of cupric carbonate, one of which was of natural origin and the other was synthetic. He found that the composition of elements present in it was same for both the sample as shown below. Thus, he concluded that irrespective of the source, a given compound always contains same element combined together in the same proportion by mass. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as law of definite compositions. Law of multiple proportion. 1.5.3 Law of multiple proportion. This law was proposed by Dalton in 1803. According to this law, if 2 elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. For example, hydrogen combined with oxygen to form 2 compounds, namely water and hydrogen peroxide. Hydrogen plus oxygen is equal to water. Hydrogen plus oxygen is equal to hydrogen peroxide. Here, the masses of oxygen is 60 grams and 32 grams, while combined with a fixed mass of hydrogen 2 grams. Where simple ratio is equal to 16:32 or 1:2. 1.5.4 Gay-Lussac Law of Gaseous Volume. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Thus, 100 ml of hydrogen combined with 50 ml of oxygen to give 100 ml of water vapor. Hydrogen plus oxygen is equal to water. Thus, the volume of hydrogen and oxygen which combine 100 ml and 50 ml bear a simple ratio of 2:1. Gay-Lussac's discovery of integer ratio in volume relationship in actually the law of definite proportion by volume. This law of definite proportion stated earlier was with respect to mass, the Gay-Lussac law was explained properly by the work of Avogadro in 1811. 1.555 Avogadro law. In 1811, Avogadro proposed that equal volume of all gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atom and molecules, which is quite understandable in present times. If we consider again the reaction of hydrogen and oxygen to produce water, we see that two volume of hydrogen combined with one volume of oxygen to give two volume of water without leaving any unreacted oxygen. Note that in figure 1.9, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If hydrogen and oxygen were considered as diatomic as recognized now, then the above results are easily understandable. However, Dalton and others believed at that time that atoms of the same kind cannot combine, and molecule of oxygen or hydrogen containing two atoms did not exist. Avogadro's proposal was published in the French journal De Physique in spite of being correct. It did not gain much support. After about 50 years, in 1860, the first international conference on chemistry was held in Karlsruhe, Germany. To resolve various ideas at the meeting, Stanislaw Canigro presented a sketch of a course of chemical philosophy which emphasized on the importance of Avogadro's work. 1.6 Dalton atomic theory. Although the origin of the idea that the matter is composed of small individual particles called atomico, meaning indivisible, dates back to the time of Democritus, a Greek philosopher 460 to 370 BC. It again started emerging as a result of several experimental studies which led to the law mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. Point 1. Matter consists of indivisible atoms. Point 2. All atoms of a given element have identical properties, including identical mass. Atoms of different elements differ in mass. Point 3. Compounds are formed when atoms of different elements combine in a fixed ratio. Point 4. Chemical reaction involve reorganization of atoms. These are neither created nor destroyed in a chemical reactions. Dalton theory could explain the law of chemical combination. However, it could not explain the law of gaseous volume. It could not provide the reason for combining of atoms, which was answered later by other scientists. 1.7 Atomic and molecular masses. After having some ideas about the term atom and molecules, it is appropriate here to understand what do we mean by atomic and molecular masses. 1.7.1 Atomic mass. The atomic mass or the mass of an atom is actually very, very small because atoms are extremely small. Today we have sophisticated techniques. Example, mass spectrometry for determining the atomic mass is fairly accurately, but in the 19th century, scientists could determine the mass of one atom relative to another by experimental means. As has been mentioned earlier, hydrogen being the lightest atom was arbitrarily assigned a mass of 1 without any units, and other elements were assigned masses relative to it. However, the present system of atomic masses is based on carbon 12 as the standard and has been agreed upon in 1961. Here carbon-12 is one of the isotopes of carbon and can be represented as 12C. In this system, 2C is assigned a mass of exactly 12 atomic mass unit AMU, and the masses of all other atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12 of the mass of one carbon-12 atom, and 1 mu is 1.66056 into 10 to the power 24 gram. Mass of an atom of hydrogen 1.6736 into 10 to the power -424 gram. Thus, in terms of AMU of the mass. Similarly, the mass of oxygen -16 atom would be 15.995 AMU. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculation, we actually use average atomic masses of elements, which are explained below. 1.7.2 Average atomic mass. Many naturally occurring elements exist as more than one isotopes. When we take into account the existence of these isotopes and their relative abundance, percent occurrence, the average atomic mass of that element can be computed. For example, carbon has the following three isotopes with relative abundance and masses at so against each of them. From the above data, the average atomic mass of carbon will come out to be. Similarly, average atomic masses for either element can be calculated in the periodic table of element. The atomic masses mentioned for different elements actually present their average atomic masses. 1.7.3 Molecular mass. Molecular mass is the sum of atomic masses of the element present in the molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains one carbon atom and 4 hydrogen atoms, can be obtained as follows. Molecular mass of methane. Similarly, molecular mass of water is 2 into atomic mass of hydrogen plus 1 into atomic mass of oxygen. Formula mass. Some substances, some as sodium chloride, do not contain discrete molecules as their constituent units. In such compounds, positive sodium ions and negative chloride ions entities are arranged in a three-dimensional structure as figured in 1.10. It may be noted that in sodium chloride, 1N plus ions is surrounded by 6 chlorine ions and vice versa. The formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state sodium chloride does not exist as a single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine. 1.8 Mole concept and molar masses. Atoms and molecules are extremely small in size, and their number in even a small amount of any substance is really very large. To handle such large number, a unit of convenient magnitude is required. Just as we denote 1 dozen for 12 items, a score for 20 items grows for 144 atoms. We use the idea of mole to count entities at the microscopic level. Atoms, molecules, particles, electrons, ions, etc. The SI system mole symbol mole was introduced as 7th base quantities for the amount of a substance. 1 mole is the amount of substance that contains as many particles of or entities as there are atoms in exactly 12 gram or 0.012 kilogram of the isotopes, it may be emphasized that the mole of a substance always contains the same number of entities, no matter what the substance may be. In order to determine this number precisely, the mass of a carbon-12 atom was determined by a number. A spectrometer are found to be equal to 1.992648 into 10 to the power minus 3 gram. Knowing that 1 mole of carbon weighs 12 gram, the number of atoms in it is equal to. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is known as Avogadro Constant or Avogadro number, denoted by Na, in honor of Avogadro. To appreciate the largeness of this number, let us write it with all zero without using any power of 10. Hence, so many entities, atom, molecules, or any other particle constituent 1 mole of a particular substance, we can therefore say that 1 mole of hydrogen atom is equal to 6.022 in power into 10 power 23 atoms. 1 mole of water molecules is equal to 6.022 into 10 power 23 water molecules. 1 mole of sodium chloride, 6.022 into 10 power 23 formula unit of sodium chloride. Having defined the mole, it is easier to know the mass of 1 mole of a substance or the constituent entities. The mass of 1 mole of a substance in gram is called its molar mass. The molar mass in grams is numerically equal to atomic molecular formula mass in U. 1.9 percentage composition. So far we were dealing with the number of entities present in a given sample, but many a time information regarding the percentage of particular element present in a compound is required. Suppose a known or new compound is given to you. The first question you would ask is, what is its formula or what are its constituents, and in what ratio are they present in the given compound. For known compound also, such information provide a check whether the given sample contain the same percentage of element as present in a pure sample. In other words, one can check the purity of a given sample by analyzing this data. Let us understand it by taking the example of water H2O. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated as follows. Mass percent of an element, mass of that element is in the compound into 100 by molar mass of the compound. (1.9.1) Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can further be obtained if the molar mass is known. The following example illustrates this sequence. (1.10) Stoichiometry and stoichiometry calculation. The word stoichiometry is derived from two Greek words, stoichion meaning element and metron meaning measure. Stoichiometry thus deals with the calculation of masses, sometimes volume also, of the reactant and the product involved in a chemical reaction. Before understanding how to calculate the amount of reactant required or the product produced in a chemical reaction, let us study what information is. is available from the balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation for this reaction is given as below. Here methane and dioxide are called reactant and carbon dioxide and water are called product. Note that all the reactant and the product are gases in the above reactions, and this has been indicated by letter G in the brackets note next to its formula. Similarly, in case of solid and liquid and are written respectively. The coefficient 2 for O2 and H2O are called stoichiometric coefficient. Similarly, the coefficient for CH4 and CO2 is 1 in each case. They represent the number of molecules and moles as well, taking part in the reaction or form in the reaction. Thus, according to the above chemical reactions, 1 mole of CH4 gram react with 2 moles of O2 gram 2 gives 1 mole of CO2 gram and 2 moles of H2O grams. 1 molecules of CH4 gram react with 2 molecules of O2 gram 2 gives 1 molecules of CO2 gram and 2 molecules of H2O grams. 22.7 L of CH4 gram react with 45.4 liter of O2 gram 2 gives 22.7 L of CO2 gram and 45.4 L of H2O grams. 16 gram of CH4 gram react with 2 into 32 gram of O2 gram 2 gives 44 gram of CO2 gram and 2 into 18 gram of H2O gram. Mass by volume is equal to density. 1.10.1 Limiting reagent. Many a time reactions are carried out with the amount of reactant that are different than the amount as required by a balanced chemical reaction. In such situation, one reactant is in more amount than the amount required by balanced chemical reaction. The reactant which is present in the least amount get consumed after some times, and after that further reaction does not take place, whatever be the amount of the other reactant. Hence, the reactant which get consumed first limits or the amount of product formed and is therefore called the limiting reagent. In performing stoichiometric calculation, this aspect is also to be kept in mind. 1.10.2 Reaction in solutions. A majority of reactions in the laboratories are carried out in solution. Therefore, it is important to understand as how the amount of substance is expressed when it is present in the solution. The concentration of a solution or the amount of substance present in its given volume can be expressed in any of the following way. 0.1 mass percent of weight percent, 0.2 mole fraction, 0.3 molarity, 0.4 molality. 0.1 mass percent, it is obtained by using the following relation. Mass percent is equal to mass of solute by mass of solution into 100. Mole fractions, it is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance are dissolved in substance B and their number of moles are N and N respectively, then the mole fraction of A and B are given as mole fraction of number of moles of A by number of moles of solutions. Molarity is the most widely used in unit E and is denoted by M. It is defined as the number of moles of the solute in 1 liter of the solution. Thus, molarity M, number of moles of solute by volume of solution in 1 liter. Suppose we have 1 M. Molarity, it is defined as the number of moles of solute present in 1 kilogram of solvent. It is denoted by M. Molarity, number of moles of solute by mass of solvent in kg. Thank you so much, guys.